Welcome back to this YouTube tutorial series on implementing generics and templates in C. In today's video, we're going to be finishing up our examples. So recently, we have just created our employee structures, as we can see here, initialized their schedules, their data of the schedules, and their names, and pushed them onto the stack. Before we pop them off, I'm going to make another employee structure called temp. Let me go back and restart this again. Temp is equal to employee pointer. Allocate the memory for it. Temp dot name. What I'm actually going to do is copy and paste this. And instead of object, it's going to be temp. We're going to say names at index 0. So I made our temporary employee, and I made its name equal to Bill. So what I'm going to do is I'm going to printf is Bill present %d. And what I'm going to do is I'm going to take our stack.contains function, pass our stack variable, and then our employee variable. So what our contains method is going to do, it's going to go through, loop through our stack, and compare the values. And using our custom comparator function, as you notice, we only use the name. We don't rely on the schedule at all. This is why I did not initialize that data. And then what I'm going to do is run this. And so we have lots of functions implicit there. So what we have to do is we have to include the string.h file. So we're going to say include string.h. Now let's compile this again. No errors. So Bill is present. Yes, he is. That's good. Now what we're going to do is we're going to say string copy temp.name with, let's say, Joey. Now Joey is not present in this names list. Therefore, he should not be present in our objects. So now when we say printf of is Joey present, we check contains, this should be a 0 because we changed the name of our employee object from Bill to Joey. So we clear this, compile, and now run. So Bill is present, yes. Joey present, no. So our comparator function works, and now what we need to do is actually go through each of our employee structures and pop them off of the stack. So we say for integer I is equal to 0, I is less than 3, I plus plus. We're going to say employee object is equal to employee object of stack.pop of my stack. So this is going to return a void pointer, and we're going to cast this back into an employee object. We're going to say printf employee, and we're going to type up their name, object.name, and we're going to print out their schedule. Now their schedule is all going to be the same, as we can see here, because we're just looping through the indices of this inner for loop. However, I'm just using this just to show that it worked. J is less than 5, J plus plus, printf %d, we're going to comma object.schedule.data, that integer j, And at the very end, we're going to print a new line. And then what we're going to do is we are simply going to call our free value function from this. And the reason why is simply because we called stack.pop. Well, what does stack.pop do? All it does is simply frees the nodes containing the values and returns the values. So we need a way of getting rid of these values. Well, we've already defined our custom destructor method for our employee structure, so we're simply just going to call this. So call it on the data, and then what we're going to do at the very end is we're going to call our stack.destructor. Or address of our stack. This returns, this passes a double pointer. Now, since we're calling pop, we're getting rid of all of the variables, all of the values inside our stack. So our size should be 0. So whenever we call our destructor, size is 0, and the only thing that's left to do is actually free the stack pointer itself. So now let's actually run this code. So Bill is present, and Joey's not, employee Anderson. Here's his schedule, William, Bill. And now what we can do is run a vol grind just to make sure everything is working. So we have 19 Alex, 17 frees. So we're actually missing some of, and I don't know exactly where that's from. That's from this temporary employee structure. So I'm going to say free temp.name and then free the structure itself. So we're going to compile this, now run it. So as we can see, we have 19 frees, 19 Alex. So everything worked there. So there we have it. We've fully implemented the stack data structure as a template, and it can hold any kind of variable. As we can see, any kind of data structure. As we can see, we've defined our own user type, but it doesn't have to be a user type. It can be a primitive type, such as an int pointer or a double pointer or such. And not just unique data structures that you define, but you can also pass in primitive types as data types. So let's make another quick example. This time we can say stack my stack2 stack.initialize. Actually, before we do that, there's one thing I'd like to show you guys. So even though we were returning a void pointer, and a void pointer can be of any type, what would happen if we actually converted this to something else? So for the purpose of this, I'm going to just comment all this out. So what would happen if we actually made this an integer pointer? So call this object. Now this is totally legal because a void pointer can take up any type. So this is actually going to run. However, what's going to happen if we actually run this? So let's do a vol grind. And we have some leaks. However, what would happen if we try to print this out? %d, and we want to dereference object to get its value. So here we're getting absolutely garbage. So this is the main problem that happens when you're using void pointers. You have to be precise in actually casting them back into their original data types. So it is bad practice, let's say in my stack, for example, to mix it with employee structures and integer pointers, because you're not going to know which is which, and whenever you cast it back into something, you're going to get complete garbage. So That's one thing to note. And as the last thing, what I'm going to do is give a quick example of just using primitive types in general. So what we can do here is we can say integer compare employee, excuse me, compare const void left, const void right. You see, integer L, dereference, and cast of left, integer R, of right. We say if L is less than R, return -1, else if L is greater than R, return 1, else return 0. So here we have it. This is how we're going to compare two integers. And how are we going to free it? We're going to say void free value, void value, and we're just going to say return. Because we're using primitive value types, we're not actually allocating any type of memory onto the heap. So there's no need to free anything. So our free value is simply going to be null. So we're going to go down here. We're going to say stack, my stack2, stack.initialize, the address of my stack2, or you know what, we don't even have to use my stack2. We can simply reinitialize our my stack. Hold on real quick, getting some kind of error. My stack, free value, and compare. And then what we can do is we can say for integer I is equal to 10, equal to 0, I is less than 10, I plus plus. We can say stack.push my stack integer I. And then what we can do, say for integer j is equal to 0, j is less than 10, j plus plus. We can print f value %d. We're going to say stack.pop my stack. Now this is going to return a void pointer, so we need to cast this into an integer pointer and then dereference it to get the value. Then we're simply going to call our stack.destructor on our original stack and add one more print statement right here just to give us some room. So here we have integer type of that. Let's cast this back. Oh, excuse me, I think that actually, wait a second. So what I need to do is actually not cast this into a void pointer, but pass its address. So we're going to treat this, we're passing the address of I, and we're going to pass that address into our void pointer. So we're going to compile this. But before I do that, I'm going to add a new line statement here. Compile it again. Perform a Valgrind check. So there we have it. So something interesting just happened. All the values of our stack are 10. And I want you guys to think of why this happened. What exactly caused this to happen? So unfortunately we're out of time right now, but in the next video I'm going to explain why this happened and give some concluding thoughts. So thank you for watching.